Imagine looking up at the sky on a clear night. Above you stretches an endless sea of stars, silent, mysterious, and full of questions that have occupied humanity for thousands of years. But how much of it do we really understand? Do you think that we already know today how the universe came into being, or are we only at the very beginning of our findings? Be sure to write your opinion in the comments below. I'm curious what you think. In this video, we embark on a journey through the history of astronomy together. From the first humans to recognize patterns in the stars, to the great breakthroughs that changed our view of the world forever. You'll see that every generation has thought they found the answers, only to discover later that the universe is much bigger, more complex, and more fascinating than previously thought. If you are interested in such topics and want to learn more about the secrets of the universe, then support the whole thing with a like and subscribe to the channel so that you don't miss any more exciting journeys through science and history. And now, let's look to the stars together and find out how it all began. Chapter 1. Looking at the sky, the beginnings of astronomy. Long before cities, writing, or organized science, the history of astronomy began with a simple but profound moment, a man's gaze at the night sky. In a world without artificial light, the sky revealed itself in all its glory, a sparkling, seemingly endless sea of stars that appeared anew every night. For early humans, this sight was not only beautiful, but also mysterious, perhaps even frightening. What were these lights? Why did they move? And what significance did they have for life on Earth? The first celestial observations were neither systematic nor scientific in the modern sense. They were characterized by amazement, intuition, and direct experience. But it is precisely in this amazement that lies the origin of all later insights. Heaven was one of the few constants in an otherwise unpredictable world. While life on Earth was constantly changing due to weather, seasons, and dangers, the sky seemed to follow a fixed order. The sun rose every morning, wandered across the sky, and disappeared in the evening. The moon changed shape regularly, and the stars returned night after night in familiar patterns. People noticed this regularity early on, and it began to play a central role in their lives. Especially for hunter-gatherers, orientation was crucial. In wide landscapes without recognizable paths or markings, the sky offered reliable help. Certain constellations served as landmarks that helped to determine directions and to find one's way even over long distances. The sky thus became a natural navigation system long before there were maps or compasses. But not only spatial orientation, but also the understanding of time was closely linked to heaven. The alternation of day and night was obvious, but over time, people also recognized longer cycles. The phases of the moon repeated at regular intervals, and the position of the sun in the sky changed throughout the year. These observations made it possible not only to experience time, but also to structure it. Especially with the transition to agriculture, this knowledge became essential for survival. Knowing when to sow and when to harvest could make or break an entire community. Heaven thus developed into a kind of calendar that determined life on Earth. Certain stars appeared in the sky only at certain times of the year, and their appearance was associated with recurring events in nature. These connections have been observed, remembered, and passed on over generations. Without writing, this usually happened through oral tradition, often embedded in stories, myths, and rituals. For early humans, heaven was not only a practical tool, but also a place full of meaning. The stars became figures, animals, gods. Constellations were created not only to make it easier to remember positions, but also to give the sky a narrative structure. These stories helped to make complex observations understandable while conveying cultural values. The sky thus became a canvas on which people's ideas and fears were reflected. In many early cultures, the observation of the sky was closely linked to religious ideas. The movements of the sun, moon, and stars were interpreted as an expression of divine powers. Particularly unusual events such as comets or eclipses were often considered signs or warnings. Those who could read the sky had a special position in the community. Shamans, priests, or early scholars took on the role of mediators between heaven and earth. They interpreted the signs in the sky and gave them meaning for people's lives. An impressive testimony to the importance of the sky in this early phase are monumental buildings, which were obviously oriented according to astronomical aspects. A well-known example is Stonehenge, whose huge stone circles are arranged in such a way that they are in line with certain sun positions, such as at the summer and winter solstice. Such structures show that people not only observed, but also began to consciously use their findings and transfer them into permanent structures. This development marks an important step, the transition from random observation to targeted targeting. Heaven was no longer just contemplated, but actively integrated into life. Places were built in such a way that they made astronomical events visible. Rituals were tied to certain celestial constellations. The cosmos became part of the social and cultural order. Despite all this progress, the understanding of heaven initially remained strongly influenced by mythology. The question of why was not answered in the scientific sense, but through stories and belief systems. But this is exactly where the basis for later development lies. People began to ask questions. Why does the moon move? Why do the stars change throughout the year? Why isn't the sky always the same? These questions led to ever closer observation. Over time, differences were recognized. Some stars moved differently than others. We now know that these are planets. The moon showed different phases. The sun changed its orbit over the course of the year. All these phenomena were registered, compared, and increasingly consciously perceived. Even without modern instruments, people developed an amazingly fine sense of the sky. Her tools were patience, attention, and experience. Over many generations, a collective knowledge was created that was constantly refined. This knowledge was not fixed in writing, but lived in the community, in stories, rituals, and traditions. What makes this early phase of astronomy special is its universality. All over the world, independently of each other, people began to observe and interpret the sky. Whether in Africa, Europe, Asia, or America, looking up was a shared human experience. Despite different cultures and ways of life, a similar need developed everywhere, to understand heaven and recognize its influence on life. This universal curiosity is still a central part of astronomy today. Even though our methods and possibilities have changed radically, the fundamental impulse remains the same, the desire to grasp the unknown. The first skywatchers laid the foundation for everything that was to follow. They had no telescopes, no formulas, and no theories, but they had questions. Chapter 1 of the History of Astronomy is therefore more than just a look into the past. It is the story of the beginning of an idea, that heaven is not only a mystery, but also a mystery that can be solved. Over time, simple observations developed into a deeper and deeper understanding. And even though the answers were initially wrapped in myths, they ultimately led to a process that continues to this day. When we look at the sky today, we do so with a completely different knowledge. We know stars as distant suns, understand the movement of the planets, and have models for the origin of the universe. But it all began with a simple moment, a person who looked up and wondered what he was actually seeing. And it is precisely this moment that connects us to our ancestors. Because no matter how far science has progressed, the view of the sky has lost none of its fascination. Chapter 2: Astronomy in the Early Advanced Civilizations. With the transition from small nomadic groups to complex, sedentary societies, people's view of the sky also began to change fundamentally. Whereas the sky had previously offered orientation and wonder, it now became a tool, something that was specifically observed, documented, and used. In the early advanced civilizations, astronomy developed from an intuitive practice to a systematic discipline that was closely interwoven with religion, politics, and everyday life. This change was closely related to the emergence of agriculture. Sedentary societies were dependent on understanding their environment precisely and planning for the long term. The right time for sowing and harvesting was crucial for the survival of entire communities. But without modern technology, there were few reliable clues to the course of the seasons. The sky offered a solution here. Its movements were regular, recurring, and with enough observation, predictable. One of the earliest and most influential cultures in this context was the Mesopotamian civilization. In the area between the Euphrates and the Tigris, people began to systematically observe the sky and record their findings over 4,000 years ago. The Babylonians kept detailed records of the positions of stars and planets and developed methods to calculate their movements. This data was written on clay tablets and passed down through generations. Remarkably, these early astronomers already recognized patterns that repeated over long periods of time. For example, they were able to predict the movements of certain planets, although they did not yet have a physical understanding of their nature. For them, these celestial bodies were not worlds, but wandering lights in the sky that followed certain rules. Nevertheless, their approach was surprisingly precise and laid the foundation for mathematical models that were later further developed. At the same time, astronomy in Mesopotamia was closely linked to astrology. Celestial events were not only observed, but also interpreted. An unusual planetary constellation could be interpreted as a sign of political upheaval, a darkness as a warning of impending disaster. The priestly astronomers, therefore, had a special position in society. They were considered mediators between heaven and earth and advised kings on important decisions. Their knowledge was power, and was protected and maintained accordingly. Heaven also played a central role in ancient Egypt, but with a slightly different focus. Here it was above all the rhythm of the Nile that determined life. The annual flood brought fertile mud and made agriculture possible on a larger scale. The prediction of this event was therefore of enormous importance. The Egyptians were guided by a very specific celestial event, the heliacal rising of the star Sirius. When Sirius reappeared in the sky for the first time shortly before sunrise after a period of invisibility, it was a reliable sign that the Nile flood was about to begin. This observation was so precise that it became the basis of a calendar. The Egyptians developed a year with 365 days, an impressive achievement for this early period. Although the fine-tuning of leap years was still missing, the system was stable enough to enable long-term planning. While practical and religious aspects dominated in Mesopotamia and Egypt, a particularly long-term and continuous tradition of observing the sky developed in China. Astronomical events have been documented there for thousands of years: comets, stellar explosions, solar and lunar eclipses. These records are invaluable today, as they represent one of the longest continuous data series in human history. In the Chinese worldview, heaven was closely linked to the political order. The emperor was considered the son of heaven, and his right to rule was seen as divinely legitimized. Changes in the sky could therefore be interpreted as a sign of the state of this order. An unexpected celestial event could sow doubts about the rule of an emperor or be understood as a warning. Astronomers thus had not only a scientific, but also a political responsibility. This responsibility led to sky observation being carried out particularly precisely and systematically. Mistakes could have serious consequences, which is why great emphasis was placed on precision. At the same time, a deep understanding of the regularity of certain phenomena developed. Here, too, a central element of early astronomy becomes apparent: the search for order in the movements of the sky. Another impressive example of the development of astronomical knowledge can be found among the Maya in Central America. Although this culture had no contact with the advanced civilizations of the Old World, it independently developed an extremely complex system of celestial observation. In particular, the movements of Venus were closely tracked and integrated into calendars. The Maya recognized the cycles of this planet with astonishing accuracy and used this knowledge for religious and social purposes. The Mayan calendars were highly developed and combined different time cycles with each other. They made it possible not only to plan rituals, but also to make long-term predictions. These systems show that astronomy was much more than mere observation. It was an integral part of cultural identity. Another important step was the development of instruments. Although these were still simple, they enabled more precise measurements. Shadow sticks, early sundials, or simple sighting aids helped to determine angles and times more precisely. These tools expanded the possibilities of observation and made it more independent of subjective impressions. Over time, a clear division of labor also emerged. Astronomy became the task of specialists, people who studied the sky intensively and passed on their knowledge within certain groups. This knowledge was often exclusive and closely linked to power structures. Those who understood the sky could make predictions, and thus influence decisions. Despite all the differences in culture and worldview, one central commonality can be identified. The sky was perceived everywhere as an orderly system. His movements followed rules that could be recognized and used. This finding was revolutionary, because it laid the foundation for later scientific astronomy. The idea that the universe is not chaotic, but structured, is one of the most important prerequisites for any form of science. Chapter 2 thus shows a decisive phase in the development of astronomy. The amazement of early humans turned into systematic knowledge. The sky was measured, documented, and interpreted. Calendars were created, predictions became possible, and the first mathematical models were developed. All of this happened long before there was a modern understanding of physics or the laws of nature. The history of astronomy is therefore not only a history of great discoveries, but also a history of patient observation and collective learning. In the early advanced civilizations, the sky was systematically explored for the first time, and this was the beginning of the long road to our current understanding of the universe. Chapter 3: Greek Antiquity, Philosophy Meets Science. Greek antiquity marks the beginning of a decisive turning point in the history of astronomy. While earlier advanced civilizations mainly observed, documented, and used the sky for practical or religious purposes, the Greeks went one step further. They wanted to understand why the sky works the way it does. Pure observation turned into theoretical thinking. Astronomy became not only a collection of data, but a field of philosophy, and thus the origin of the scientific explanation of the world. At the heart of this change was a new way of thinking. The Greek philosophers were looking for rational explanations for natural phenomena. They no longer wanted to resort solely to myths or divine intervention, but believed that the universe was built according to certain principles that the human mind could recognize. This attitude was revolutionary. It laid the foundation for what we now understand as science. One of the first to try to explain the universe systematically was Aristotle. For him, the universe was an ordered hierarchical system with the Earth at its center. This so-called geocentric view of the world assumed that all celestial bodies, sun, moon, planets, and stars, move around the Earth on perfect, circular orbits. The circle was considered the most perfect form, and therefore the sky had to be perfect. Aristotle distinguished between two areas of the universe: the sublunar world below the moon, which consisted of the four elements earth, water, air, and fire, and was subject to change, and the supralunar world above, which was unchanging and perfect. In his view, the celestial bodies consisted of a fifth element, the so-called ether, and moved in an eternal uniform circular motion. This idea was not only philosophically convincing, but also intuitively comprehensible. After all, the Earth seemed to stand still while the sky moved above it. But although this model was elegant, it had a problem. The actual movements of the planets in the sky did not fit perfectly. Some planets seemed to change direction, move backwards, and then resume their original course. This so-called retrograde puzzled observers. To explain these irregularities, increasingly complex models have been developed. This is where Ptolemy comes into play, who in the 2nd century AD developed a system that would remain the dominant worldview for over 1,000 years. In his work Almagest, he described a detailed geocentric model that could predict the observed movements of celestial bodies with astonishing accuracy. His approach was based on so-called epicycles, small circular motions that lay on larger circular paths. By combining several such motions, he succeeded in explaining the apparent irregularities of the planetary orbits. The Ptolemaic system was mathematically complex, but extremely successful. It showed that geometry and calculation could be used to model the movements in the sky. This was a decisive step. Astronomy became a mathematical science. Observations were not only described, but translated into formulas and models. But Greek astronomy did not only consist of the geocentric view of the world. There were also thinkers who developed alternative ideas. One of them was Aristarchus of Samos, who proposed a heliocentric model as early as the 3rd century BC, that is, the idea that the sun is in the center and the earth moves around it. This idea was far ahead of its time, but it did not catch on. It contradicted everyday experience and did not fit into the philosophical worldview, which saw the earth as the center of the universe. Another important contribution of the Greeks was the realization that the earth is a sphere. This idea was supported, among other things, by observations of lunar eclipses, in which the Earth's shadow always appears round on the Moon. The different constellations that can be seen depending on the geographical position also indicated that the Earth could not be a flat disk. Particularly impressive is the work of Eratosthenes, who calculated the circumference of the Earth with astonishing accuracy in the 3rd century BC. He took advantage of the different positions of the Sun in 2 cities, Syene and Alexandria, and combined this observation with geometric considerations. The result was surprisingly close to the actual value. This achievement shows how far the combination of observation and mathematics had already been developed. Greek astronomy was thus characterized by a new way of thinking, the attempt to understand the world through logic, geometry, and systematic analysis. The idea that the universe works according to fixed laws also played a role. These laws had not yet been formulated in the modern sense, but the foundation had been laid, the conviction that natural phenomena can be explained. Another important aspect was the development of models. The Greeks understood that complex observations could be described by simplified representations. These models did not necessarily have to depict the truth, but above all explain the observations and make them predictable. This approach is still a central part of science today. At the same time, astronomy remained closely linked to philosophy. Questions about the structure of the universe have always been questions about the order of the world and man's place in it. The geocentric worldview was not only a scientific model, but also an expression of a certain understanding of the world in which the human being was at the center. Greek antiquity thus produced a decisive innovation, the combination of observation, mathematics, and theory. While earlier cultures described and used the sky, the Greeks tried to explain it. They asked questions, developed models, and looked for general principles. Even if many of their ideas are not correct from today's perspective, their influence was enormous. The geocentric worldview of Aristotle and Ptolemy was to remain the basis of astronomy for many centuries. It was not until the early modern period that it was called into question by new findings. But without Greek antiquity, this progress would hardly have been possible. It provided the tools, the mindset, and the methods that were later further developed. The idea that you can not only observe the sky, but also understand it, was born during this time. Chapter 3 therefore shows not only an epoch of history, but a fundamental change in the thinking of mankind. The amazement at the sky turned into an attempt to explain it. Observation became theory, and philosophy slowly gave rise to what we call science today. This transition was perhaps one of the most important steps in the entire history of astronomy, because it made the sky something that can not only be admired, but also understood. Chapter 4: Astronomy in the Middle Ages, Preservation, Expansion, and New Horizons. With the end of antiquity and the collapse of the Western Roman Empire, the development of the sciences also changed fundamentally. The Middle Ages are often wrongly portrayed as a time of stagnation, but especially in astronomy it was rather a phase of preservation, further development, and cultural networking. While in Europe many ancient writings were initially forgotten, in other parts of the world they were not only preserved, but actively studied, expanded, and critically questioned. The Islamic world in particular played a central role during this time. Between the 8th and 14th centuries, an impressive scientific network developed there, reaching from Spain to Central Asia. In cities such as Baghdad, Damascus, or Cordoba, centers of knowledge were created in which scholars from different cultures came together. One of the most important institutions was the so-called House of Wisdom in Baghdad, a kind of early research center where ancient works were translated and commented on. Here, among other things, the writings of Aristotle and Ptolemy were translated into Arabic and intensively studied. But the scholars were not content with preserving this knowledge. They continued to develop it. They reviewed the existing models, improved calculations, and carried out their own observations. This resulted in a new dynamic form of astronomy based on the combination of tradition and innovation. An important representative of this era was Al-Battani, who lived in the 9th and 10th centuries. He greatly improved the accuracy of astronomical measurements and corrected some of the values that were still from ancient times. His calculations on the length of the solar year and the inclination of the Earth's axis were remarkably precise and were later adopted in Europe. Such work shows that astronomy in the Middle Ages was by no means stagnating, but was actively advancing. Another important advance was the development and improvement of astronomical instruments. The astrolabe, a versatile device for determining star positions, time and latitude, was perfected and widely used during this time. It made it possible not only to observe the sky, but also to measure it concretely and derive practical applications from it, for example, for navigation or the determination of prayer times. Religious practice actually played an important role in medieval astronomy. In Islam, it was necessary to determine the prayer times exactly and to calculate the direction to Mecca. These requirements led to an intensive study of celestial movements and geographical calculations. It was similar in Christian Europe, where the ecclesiastical calendar, especially the calculation of the date of Easter, required precise knowledge of astronomical cycles. While the Islamic world played a leading role during this time, from a high Middle Ages onwards a stronger interest in science and astronomy began to develop again in Europe. A decisive factor was the retranslation of Arabic texts into Latin, especially in cities like Toledo. As a result, not only the ancient works came back to Europe, but also the expanded knowledge of Islamic scholars. This rediscovery led to the founding of the first universities and to a new form of knowledge organization. Astronomy became part of the so-called quadrivium, one of the 7 liberal arts, and thus an integral part of academic education. Nevertheless, she remained closely connected to philosophy and theology. The geocentric view of the world continued to be regarded as a basis, as it was well compatible with religious ideas. Despite this attachment to traditional models, some scholars began to think critically and question existing assumptions. They noticed inaccuracies in the calculations and looked for better explanations for the movements of the celestial bodies. Although these considerations did not yet lead to a fundamental upheaval, they prepared the ground for later developments. An important aspect of this period is the increasing precision of observations. Observatories were built in various regions that were specially designed for sky observation. These facilities made it possible to collect and systematically evaluate data over longer periods of time. The accuracy of these measurements often exceeded that of antiquity and formed an important basis for the later scientific revolution. Astronomy has also been further developed in other parts of the world, such as India or China. In China, the long tradition of observing the sky continued, and detailed records of astronomical events continued to be kept. This global perspective shows that the development of astronomy was not an isolated process, but an interplay of different cultures and knowledge systems. What particularly distinguishes the Middle Ages is its role as a bridge between antiquity and modern times. During this time, the knowledge of the past was not only preserved, but also expanded and passed on. Without this phase of transmission and further development, many ancient knowledge would have been lost, and the later scientific revolution could hardly have taken place. At the same time, the Middle Ages also showed the close connection between knowledge and worldview. Astronomy was not only a science, but also part of a comprehensive understanding of the world that combined religious, philosophical, and cultural aspects. Heaven was not only an object of investigation, but also a symbol of order, harmony, and divine structure. But it was precisely in this connection that there was also a certain limitation. New ideas often had to move within existing systems of thought and could not be developed freely. Nevertheless, Important impulses arose in this field of tension that were later to lead to fundamental changes. Chapter 4 thus shows an often underestimated phase of astronomy history. It is the time when knowledge was preserved, networked, and gradually expanded. A time in which different cultures exchanged ideas with each other and worked together on a better understanding of heaven. When we look back at the Middle Ages today, we realize that progress does not always happen in leaps and bounds. Sometimes it's the quieter phases, collecting, translating, improving, and sharing knowledge, that make all the difference. Astronomy in the Middle Ages was just such a phase, not a standstill, but a foundation. And on this foundation, one of the greatest upheavals in the history of science was soon to emerge. Chapter 5, The Copernican Revolution, a new worldview emerges. For many centuries, mankind's worldview seemed to be fixed. The Earth rested at the center of the universe, and all celestial bodies moved in perfect orbits around it. This geocentric model, shaped by the teachings of Aristotle and mathematically elaborated by Ptolemy, was not only scientifically accepted, but also deeply rooted in religious and philosophical ideas. It corresponded to everyday experience. After all, no one felt that the Earth was moving, and gave humans a central position in the cosmos. But in the 16th century, this seemingly unshakable worldview began to falter. The trigger for this change was a man who at first hardly caused a stir, Nicholas Copernicus. As a canon, mathematician, and astronomer, he dealt intensively with the existing models of planetary motion, and encountered a fundamental problem. The calculations of the Ptolemaic system became more and more complicated, as more and more epicycles had to be added to explain the observed movements. The model worked, but it seemed increasingly artificial and confusing. Copernicus therefore asked himself a radical question. What if the focus is not on the Earth, but on the Sun? This idea was not entirely new. There had already been similar considerations in Antiquity, but Copernicus systematically developed it further. In his work De Revolutionibus Orbium Coelestium, published in 1543, he presented a heliocentric view of the world in which the Sun is at the center and the Earth moves around it together with the other planets. The Earth was thus no longer the center of the universe, but itself one celestial body among many. This idea had far-reaching consequences. Suddenly, many previously mysterious phenomena could be explained more easily. The apparent backward movement of the planets was not a real regression, but a consequence of the different orbital speeds of the planets around the Sun. The brightness fluctuations of the planets also suddenly made sense. They appeared brighter or darker, depending on how far away they were from Earth. Despite these advantages, the heliocentric model was not clearly superior at first. Copernicus continued to hold on to the idea that the planets move in perfect circular orbits, and therefore had to introduce complex additional motions as well. Nevertheless, his approach was revolutionary, not because of its immediate accuracy, but because of its perspective. He shifted the center of the universe and thus called into question the entire worldview. The publication of his work came at a time of great upheaval. The Renaissance had reignited interest in ancient knowledge, and the printing press allowed ideas to spread more quickly. At the same time, the Church was a dominant authority, and new ideas had to be compatible with existing religious teachings. The heliocentric worldview was in tension with the traditional interpretation of religious texts, which saw the Earth as the center of creation. Nevertheless, Copernicus' work was initially regarded as a mathematical model rather than a physical reality. Many scholars used his calculations without accepting his basic assumption. The heliocentric system was a tool, but not yet a universally accepted truth. A decisive step in the development of this new view was the increasing importance of observation and measurement. While ancient astronomy was strongly influenced by philosophical considerations, the focus now shifted more strongly to empirical data. More precise observations made it possible to critically review and improve models. In this context, it also became clear that the geocentric worldview was not as stable as long assumed. Small deviations between calculations and actual observations accumulated. While these inaccuracies were often minor, they showed that the existing model was not perfect. The heliocentric system offered an alternative perspective that simplified many of these problems. At the same time, the Copernican Revolution was not only a scientific but also a philosophical challenge. If the Earth was no longer at the center, what did that mean for man's position in the universe? Was man still the center of creation, or just a part of a much larger whole? These questions went far beyond astronomy and touched fundamental ideas about the nature of reality. The reactions to these new ideas were mixed. Some scholars were fascinated by the elegance of the heliocentric model, others firmly rejected it. Particularly problematic was the lack of direct observation of the Earth moving. If the Earth was actually moving, why didn't you feel it? Why did objects fall vertically down instead of remaining at an angle? Such questions could not yet be answered satisfactorily in Copernicus' time. Despite these open problems, the idea slowly caught on. Not as an immediately accepted truth, but as an approach that opened up new possibilities. She called for existing assumptions to be questioned and alternative explanations to be considered. This is precisely the real significance of the Copernican Revolution. It changed not only a model, but the way people thought about the universe. Another important aspect was the increasing separation of authority and knowledge. While ancient philosophers or religious texts used to be considered inviolable sources, people now began to give greater weight to their own observations and calculations. Truth was no longer derived exclusively from tradition, but was increasingly determined by examination and proof. This development was the beginning of a new scientific attitude. Doubt became an important tool, and progress came from questioning existing ideas. The heliocentric view of the world was a catalyst, an idea that inspired others to think ahead and break new ground. Chapter 5 thus marks one of the most significant turning points in the history of astronomy. It is the moment in which the view of the universe changes fundamentally. The Earth is losing its central position, and man is beginning to see himself as part of a larger system. But this revolution was not a sudden upheaval, but a slow process. It took decades for the new ideas to catch on, and even longer for them to be fully accepted. Nevertheless, the foundation stone was laid. The door to a new understanding of the cosmos was opened. The Copernican Revolution impressively shows how a single idea can change the world. Not because it provides all the answers immediately, but because it asks the right questions. And it is precisely these questions that should be continued in the following chapters, by new observations, new theories, and an ever deeper understanding of the universe. Chapter 6: The Struggle for Truth, Galileo, and the New View of Heaven. The ideas of Nicholas Copernicus had laid the foundation for a new worldview, but at first they remained mainly theoretical. There was a lack of convincing evidence that clearly supported the heliocentric model. This is exactly where the story of a man begins, who stands for the transition to modern science like no other, Galileo Galilei. Galileo was not only a brilliant thinker, but also a passionate observer. In contrast to many of his predecessors, he did not rely exclusively on mathematical models or philosophical considerations, but relied on direct observation and experimental verification. In doing so, he embodied a new kind of scientist, someone who not only wanted to understand nature, but also to measure and test it. A decisive moment in Galileo's life came at the beginning of the 17th century, when he heard about a new invention, the telescope. Originally developed in the Netherlands, it was initially used for military purposes. However, Galileo immediately recognized the potential of this instrument for observing the sky. He improved the design and finally aimed it at the night sky, with consequences that were to change humanity's view of the world permanently. What he saw contradicted the ideas of Antiquity in many respects. The moon was not a perfect, smooth sphere, but characterized by mountains and valleys. The surface seemed rough and uneven, similar to the Earth. This called into question one of the central assumptions of the Aristotelian worldview, namely the idea that heaven is perfect and unchanging. Even more important were Galileo's observations of the planet Jupiter. He discovered 4 small celestial bodies orbiting him, now known as the Galilean moons. This discovery was revolutionary because it showed that not everything in the universe revolved around the Earth. So there were other centers of movement as well. This simple but powerful argument directly challenged the geocentric worldview. Another crucial piece of evidence for the heliocentric model was the phases of Venus. Galileo observed that Venus, similar to the Moon, goes through different phases. These phases can only be explained if Venus orbits the Sun, and not the Earth. Galileo thus provided one of the first direct indications that the Copernican system was closer to reality than the traditional model. The Sun itself also turned out to be less perfect than had long been assumed. Galileo discovered sunspots, dark areas on the surface of the Sun that changed and moved. This observation showed that even the Sun was not immutable, but was subject to dynamic processes. Once again, a central assumption of the old worldview was shaken. But Galileo's work was not only a series of spectacular discoveries. It also represented a fundamental change in the way knowledge is obtained. He combined observation, experiment, and mathematics into a new method that later became the basis of modern science. For Galileo, it was crucial that statements about nature had to be verifiable. Authority alone, whether that of a philosopher or a religious institution, was not sufficient proof. However, this attitude brought him into conflict with the Church. The geocentric worldview was deeply rooted in the theological tradition and was seen as compatible with the Scriptures. The heliocentric model, on the other hand, called this order into question. It shifted not only the position of the Earth, but also that of man in the universe. At first, Galileo tried to find a balance. He argued that the Bible should not be understood as a science textbook and that its statements should be interpreted in context. But his increasing public support for the heliocentric worldview made him a controversial figure. The conflict finally escalated when Galileo published his work Dialogue on the Two World Systems. In this book, he contrasted the geocentric and heliocentric models, but in a way that made the Copernican system appear clearly superior. This was understood by the Church as a provocation. In 1633, Galileo was summoned to appear before the Inquisition. In a famous trial, he was forced to publicly revoke his support for the heliocentric worldview. He spent the rest of his life under house arrest. Despite this personal defeat, his work had already had an effect that could no longer be reversed. Galileo's observations had permanently shaken confidence in the geocentric view of the world. They showed that reality was more complex than the traditional models suggested. Above all, however, they made it clear that direct observation is a crucial key to understanding the universe. His legacy lies not only in his discoveries, but in his method. The idea that knowledge is gained through systematic observation, experimentation, and critical thinking has become a central principle of science. Galileo is therefore often referred to as one of the founders of modern science. Chapter 6 thus tells not only the story of a conflict, but also the story of a transition. It is the moment when science breaks away from old authorities and begins to go its own way. The sky is no longer just interpreted, but examined. Hypotheses are no longer just believed, but tested. This change was not easy and not without resistance. But it was necessary to achieve a deeper understanding of the universe. Galileo showed that progress often means challenging existing beliefs, even if it is uncomfortable or dangerous. His famous saying attributed to him, "And yet she moves," sums up this attitude. Even though he was forced to publicly recant his beliefs, the truth remained. The Earth is moving, and with it the thinking of humanity began to change. With Galileo, astronomy finally becomes an empirical science. His work paves the way for further great discoveries and theories that would continue to deepen our understanding of the universe. The fight for the truth was not over, but it had taken a new direction. Chapter 7: The Laws of Planetary Motion, Order in the Chaos of Heaven. After Nicholas Copernicus had proposed the heliocentric view of the world and Galileo Galilei had provided the first convincing observations, one crucial element was still missing: a precise mathematical description of the planetary movements. Although it had become clear that the Earth and the other planets move around the Sun, exactly how these movements take place was still a mystery. The previous models were either too complicated or not accurate enough. It is precisely at this point that one of the most important figures in the history of astronomy enters the stage: Johannes Kepler. Kepler was an extraordinary thinker who combined science, mathematics, and a deep search for cosmic harmony. Unlike many of his contemporaries, he was not only interested in the description of celestial movements, but also in the underlying laws. For him, the universe was not a chaotic system, but an ordered structure that can be explained by mathematical principles. A decisive influence on Kepler's work was the Danish astronomer Tycho Brahe, who had collected extremely precise observational data over decades. At the time, this data was the most accurate available, and it presented an enormous challenge. This is because they do not fully fit the existing models, neither the geocentric nor the Copernican system. Kepler quickly realized that this was the key to a deeper understanding. The planet Mars in particular caused difficulties. Its orbit deviated significantly from the expected calculations. Kepler spent years analyzing these deviations. Again and again he tried to explain the data with circular orbits, but he did not succeed. Finally, he made a radical decision. He gave up the idea that planets must move in perfect circles. Instead, he discovered that the planets move on ellipses, i.e., on slightly elongated circular shapes in which the Sun is not in the center, but in one of the two focal points. This realization was revolutionary. She contradicted the millennia-old belief that the circle is the only perfect shape for celestial movements. But it fit perfectly with the observation data. This discovery became the first of Kepler's three famous laws of planetary motion. It states that the planets move on elliptical orbits around the Sun. This was the first model to be found that could describe the actual movements of the planets with high accuracy. But Kepler went even further. He found that the planets do not move at a constant speed. Instead, they move faster when they are closer to the Sun and slower when they are farther away. This observation led to his second law, the so-called area theorem. It states that a planet sweeps over areas of equal size in equal periods of time, regardless of where it is on its orbit. This law was particularly important because it showed that the motion of the planets is not uniform, but dynamic. The speed changes depending on the distance to the Sun. This is another step away from the idea of a static, perfect sky, towards a system that is characterized by forces and changes. Kepler's third law finally established a connection between the orbital period of a planet and its distance from the Sun. It states that the square of the orbital period is proportional to the third power of the mean distance to the Sun. Simply put, the farther away a planet is from the Sun, the longer it takes to complete an orbit, and this relationship follows a clear mathematical rule. With these three laws, Kepler achieved something completely new. He described the movements of the planets not only qualitatively, but quantitatively. His laws were precise, verifiable, and universally valid. They applied not only to a specific planet, but to the entire solar system. But as impressive as these findings were, they did not yet answer the fundamental question: why do the planets move in this way? Kepler could describe the movements, but not explain them. He suspected that some kind of force emanates from the Sun that influences the planets, but he could not formulate this idea mathematically. Nevertheless, his work was a decisive breakthrough. It showed that the universe is not only observable, but also calculable. The movements of the celestial bodies follow rules that can be expressed in mathematical formulas. This finally made astronomy an exact science. Kepler's laws also had a deeper philosophical meaning. They showed that nature does not necessarily have to follow our ideas of perfection. The circle was long considered the ideal shape, but the reality turned out to be more complex. The ellipse, less perfect in the classical sense, was the actual shape of the planetary orbits. This insight is emblematic of the change in scientific thinking, away from idealized ideas and towards an orientation towards observable facts. Another important aspect of Kepler's work is the connection between theory and data. While earlier models were often based on philosophical assumptions, Kepler consistently relied on observations. He was willing to question and adjust his own beliefs if the data showed otherwise. This attitude is still a central component of scientific work today. Kepler's influence extended far beyond his own time. His laws formed the basis for the work of Isaac Newton, who would later explain the physical causes behind planetary motions. Without Kepler's precise descriptions, this next step would hardly have been possible. Chapter 7 thus marks a pivotal moment in the history of astronomy. It is the point at which observation and theory emerge into a closed system, a system that not only describes but predicts. The movements of the planets are no longer a mystery, but follow clear, mathematical laws. But perhaps even more important is the insight behind these laws, that the universe follows an order that we can understand. This order is not always intuitive, not always easy, but it is accessible. With the right tools, with patience and with the willingness to let go of old ideas. Kepler has shown that even in the apparent chaos of the sky, there is a deeper structure hidden, a structure waiting to be discovered. And it is precisely this discovery that brings us a little closer to understanding our place in the universe. Chapter 8: Gravity Explains the Universe. Newton's Revolutionary Insight. With the work of Johannes Kepler, it was possible to describe the motions of the planets with impressive accuracy. The planets followed clear mathematical laws, their orbits were predictable, and their positions could be predicted. But one crucial question remained unanswered. Why do the planets move the way they do? What keeps them on their tracks? What force is at work in the background? The answer to these questions should come from one of the most important scientists in history, Isaac Newton. With his work, it was possible for the first time to connect the movements in the sky with the processes on Earth, and thus to formulate a universal law of nature that affects the entire universe. Newton lived in the 17th century, a time when scientific thinking was developing rapidly. The ideas of Copernicus, Galileo, and Kepler had already fundamentally changed the worldview. But Newton went one step further. He didn't just want to describe how things move, he wanted to understand why they move. One of the most famous stories about Newton, whether it happened exactly like that or not, tells of an apple falling from a tree. Newton is said to have wondered why the apple always falls downwards and not to the side or upwards. This seemingly simple observation led to a profound realization. The same force that pulls the apple toward Earth could also be responsible for the movement of the moon and planets. This idea was revolutionary. Until then, the movements on Earth and the movements in the sky had been considered fundamentally different. The sky was considered perfect and unchanging, while the Earth was characterized by chaos and change. Newton, however, realized that the same physical laws apply everywhere, both on Earth and throughout the universe. From this realization, he developed the law of universal gravitation. It states that all masses in the universe attract each other. The strength of this attraction depends on the mass of the objects and their distance from each other. The larger the masses and the smaller the distance, the stronger the gravitational pull. With this law, Newton was able to explain for the first time why the planets move on their orbits. The Sun exerts a gravitational pull on the planets, which keeps it on its orbit. At the same time, their movement ensures that they do not simply crash into the Sun, but orbit it on stable paths. The elliptical orbits that Kepler had described could now be explained physically. But Newton's achievement went far beyond explaining the planetary motions. He also developed the foundations of classical mechanics, a system of laws that describes how bodies move under the influence of forces. His 3 laws of motion are still a central component of physics today. The first law, the law of inertia, states that a body remains at rest or moves uniformly as long as no force acts on it. The second law describes the relationship between force, mass, and acceleration. And the third law, actio equals reactio, states that every force produces an equally large counterforce. These laws made it possible to calculate movements precisely, not only in the sky, but also on Earth. Whether it's a falling apple, a moving chariot, or an orbiting planet, they all follow the same basic principles. Another important aspect of Newton's work was the mathematical formulation of his theories. He developed, independently of others, calculus, a new mathematical tool that made it possible to describe changes and movements exactly. This method was crucial to understanding the complex relationships between force, motion, and time. Newton published his findings in 1687 in his work Philosophiae Naturalis Principia Mathematica, or Principia for short. This book is considered one of the most influential works in the history of science. It combined observation, mathematics, and theory into a comprehensive system that explained the behavior of the universe. The impact of this work was enormous. For the first time, they had a model that could not only describe the movements of celestial bodies, but also predict them, with an accuracy that was previously unimaginable. Astronomy thus became an exact science based on clear, verifiable laws. But Newton's theory also had philosophical consequences. She showed that the universe functions according to fixed, universal laws, independent of human perception or religious interpretation. The cosmos was not a mysterious place controlled by divine intervention, but a system determined by natural laws. However, this did not mean that religion or spirituality disappeared. Rather, the perspective changed. Many saw the laws of nature themselves as an expression of divine order. The universe was understood as a kind of mechanical system that works according to precise rules, a clockwork that has been set in motion once and has been running reliably ever since. This idea shaped the thinking of the Enlightenment and influenced not only science, but also philosophy and society. The belief in reason, order, and regularity became a central principle. Despite its success, Newton's theory was not free of questions. What exactly is gravity? How does it work over great distances, seemingly without a visible medium? Newton himself could not answer these questions. He described the effect of gravity, but not its cause. Nevertheless, his theory remained the dominant model for describing the movements in the universe for centuries. It was not until the 20th century that it was supplemented by new findings and partially corrected. But its fundamental importance remained. Chapter 8 thus marks one of the greatest breakthroughs in the history of astronomy and science as a whole. With Newton, the universe became a place that could not only be observed, but understood. The movements of the celestial bodies were no longer a mystery, but the result of clear, mathematically formulated laws. This realization fundamentally changed the view of the cosmos. Heaven was no longer an area of its own mysterious rules, but part of a unified system that followed the same principles everywhere. Earth and heaven were not separated, but connected. Newton showed that the same forces that drop an apple also keep the planets in their orbits. This combination of everyday experience and cosmic order is perhaps one of the most impressive achievements of science. It shows that the universe is not only large and complex, but also understandable, if you ask the right questions and use the right tools. And this is exactly what makes Newton's work so important to this day. It opens up access to a universe that not only exists, but can be explained. Chapter 9: New Instruments, New Worlds, the Expansion of the Visible Universe. With the groundbreaking findings of Isaac Newton, the universe had become explainable by fundamental laws of nature for the first time. The movements of the planets could be calculated, their orbits predicted, and their dynamics understood. But despite these tremendous advances, one crucial limit remained: the range of the human senses. The view of the sky was still limited to what the naked eye could grasp, and that was only a tiny section compared to the actual size of the universe. This is exactly where a new phase of astronomy begins, in which not only new ideas, but above all new tools were to revolutionize the understanding of the cosmos. Instruments became the key to exploring the sky not only more closely, but also deeper. With them, the visible universe began to expand dramatically. The development of telescopes played a central role in this. Galileo Galilei had already shown the potential of enlarging the sky. But the early telescopes were still limited. They delivered blurred images and suffered from optical errors. Over time, however, these instruments have been continuously improved. New lens systems, larger apertures, and more precise designs made it possible to make increasingly detailed observations. A decisive advance came with the development of reflecting telescopes, in which light is not refracted by lenses, but reflected by mirrors. This design had several advantages. It reduced optical distortion and made it possible to build much larger telescopes. This allowed more light to be collected, and this is crucial to make faint and distant objects visible. With these improved instruments, astronomers began to rediscover the sky. Stars that had previously appeared as individual points of light turned out to be complex systems. Nebula-like structures became visible, which were initially mysterious. Some thought they were clouds within our own galaxy. Others suspected that they could be separate island universes, an idea that could not be proven at the time. A particularly significant moment in this phase was the discovery of a new planet, Uranus, in 1781 by astronomer William Herschel. Until then, only the planets that are visible to the naked eye were known. Uranus was the first planet to be discovered with the help of a telescope, a clear sign that there was much more to discover in the universe than previously thought. This discovery had far-reaching consequences. It showed that the solar system is larger than thought and that there may be other unknown celestial bodies. In fact, the close observation of Uranus later led to the discovery of Neptune, a planet whose existence was first mathematically predicted and only then observed. This was a powerful example of how theory and observation can work hand in hand. At the same time, the technique of observing the sky also continued to develop. Astronomers began to systematically map the entire sky. Star catalogs were created in which the positions, brightnesses, and movements of thousands of stars were recorded. These catalogs made it possible to track changes over long periods of time and identify new patterns. Another important advance was the introduction of astrophotography in the 19th century. For the first time, celestial objects could not only be observed, but also permanently recorded. Photographic plates were more sensitive than the human eye and could collect light over a longer period of time. This revealed details that had previously been hidden. Astrophotography fundamentally changed astronomy. It made observations more objective, reproducible, and accurate. At the same time, it opened up new possibilities for analysis. Astronomers were able to compare images, document changes, and discover new objects that had previously been overlooked. But perhaps even more important was the development of spectroscopy, a method by which the light of celestial bodies is broken down into its components. By analyzing this light, astronomers were able to gain information about the composition of stars for the first time. They discovered that stars are made of the same elements as Earth, mainly hydrogen and helium. This realization was revolutionary. It showed that the laws of physics apply not only on Earth, but in the entire universe. Heaven was no longer a strange, unreachable place, but part of the same material reality. Astronomy thus became astrophysics, a science that describes not only where things are, but also what they are and how they work. With these new tools and methods, the image of the universe began to change rapidly. The sky was no longer just a collection of points of light, but a complex system of stars, nebulae, planets, and other structures. Each new observation brought with it new questions and new opportunities to find answers. The role of astronomers also changed. They were no longer just observers, but increasingly also technicians, engineers, and physicists. The construction and improvement of instruments became a central part of their work. Large observatories were created, often in remote places with a clear view of the sky. These institutions became centers of research and enabled cooperation across national borders. Chapter 9 thus shows a phase of transition from classical astronomy, which focused on positions and motions, to a modern science that studies the universe in all its aspects. Instruments became extensions of human perception and made the invisible visible. But perhaps the most important insight of this time is a very fundamental one: that our knowledge always depends on our possibilities. With better tools, we see more and understand more. Every new technology opens up new perspectives and broadens our horizons. The history of astronomy is therefore also a history of instruments. Without telescopes, cameras, and spectrometers, many of the great discoveries would not have been possible. They are not only tools, but crucial prerequisites for progress. With Chapter 9, we reach a point where the universe begins to show itself in all its diversity. New worlds are discovered, new structures are visible, and the boundaries of the known continue to shift. But with every answer, new questions arise. How big is the universe really? Are there more galaxies? And what is beyond what we can see? These questions lead us to the next chapter, to a time when the universe was to become much larger than anyone had ever imagined. Chapter 10: Astronomy in the 19th Century, From Observing to Understanding the Stars. In the 19th century, astronomy reached a new stage of development. While in the centuries before the focus was mainly on the movements of celestial bodies, the focus now increasingly shifted to their physical nature. It was no longer just about where stars are or how they move, but about what they actually are. This marked the beginning of a profound transformation. Classical astronomy became modern astrophysics. This development was made possible mainly by two decisive advances: spectroscopy and astrophotography. Both technologies opened up completely new ways to study the sky, not only visually, but analytically. Spectroscopy is based on the insight that light is more than just brightness. When light is sent through a prism or a grid, it is split into its different colors. A spectrum is created. But this spectrum is not uniform. It contains characteristic lines, so-called spectral lines, which act like a fingerprint. Each chemical substance produces its own pattern of such lines. In the 19th century, scientists realized that the composition of celestial bodies could be determined by analyzing these spectra. That was a revolutionary realization. For the first time, it was possible to find out about the nature of stars without ever touching them. A significant contribution to this development came from Joseph von Fraunhofer, who discovered dark lines in the solar spectrum, now known as Fraunhofer lines. Later, it was understood that these lines are caused by certain elements that absorb light in a very specific way. This made it clear that the Sun consists of the same elements as the Earth. This realization had enormous implications. It showed that the laws of physics are universal. The same elements and processes that we know on Earth also exist in the stars. Heaven was no longer a strange place, but part of the same material reality. At the same time, astrophotography continued to develop. Photographic plates were able to collect light over a longer period of time and thus make details visible that escape the human eye. Stars, nebulae, and galaxies could now not only be observed, but also permanently recorded. This enabled a new form of analysis. Images could be compared, changes documented, and structures examined in more detail. Another important advance was the classification of stars. Astronomers began to rank stars according to their brightness, color, and spectrum. It turned out that stars are not all the same, but differ in temperature, size, and composition. This finding led to the development of star catalogs and later to systematic classification systems. A central figure in this field was Annie Jump Cannon, who developed a system for classifying stars according to their spectra. This system, known as the OBAFCM classification, is still used today. It ranks stars according to their surface temperature and color, making it possible to better understand their properties. As the amount of data has increased, it has also become clear that stars change over time. They arise, develop, and finally die. This realization was another step away from the idea of an unchanging sky. Stars became dynamic objects with their own life story. An important milestone in this context was the so-called Hertzsprung-Russell diagram, which was developed by Ejner Hertzsprung and Henry Norris Russell. It shows the connection between the brightness and temperature of stars and makes it clear that stars follow certain evolutionary phases. This diagram is still one of the most important tools in astrophysics today. The measurement of distances in the universe also made great progress in the 19th century. With the help of so-called parallax, a method in which the apparent displacement of a star is measured from different observation positions, reliable distances to nearby stars could be determined for the first time. This made it clear how enormous the universe actually is. Another important area was the study of nebulae. For a long time, it was unclear whether these were gas clouds within our own galaxy or independent systems. Improved telescopes and photographic methods provided ever more detailed images, but the final clarification of this question would not take place until the 20th century. Nevertheless, it became clear in the 19th century that the universe is far more complex than previously assumed. It consists not only of individual stars, but of huge structures that are connected to each other. This finding paved the way for later discoveries about galaxies and the structure of the cosmos. The role of astronomers also changed considerably during this time. They were no longer just observers, but increasingly also physicists and analysts. Astronomy became interdisciplinary and combined findings from chemistry, physics, and mathematics. This development led to an ever deeper penetration of the universe. Chapter 10 thus shows a decisive phase of the transformation. Astronomy becomes astrophysics, a science that not only describes but explains. Stars are no longer mysterious points of light, but physical objects with clearly defined properties. But perhaps the most important insight of this time is a fundamental one, that the universe is not only big, but also understandable. With the right methods and tools, we can unlock its secrets, step by step. This development laid the foundation for the great discoveries of the 20th century. Because only with the understanding of the stars did it become possible to understand the universe as a whole. And that's exactly what the next chapter will be about. The realization that our universe is much larger than anyone had ever imagined. Chapter 11. The universe gets bigger, galaxies, expansion, and a new dimension. Until the early 20th century, many astronomers believed that the universe was essentially made up of our own galaxy, the Milky Way. The stars that were seen in the sky were understood as part of a single huge system that makes up the entire cosmos. Although there were already indications of so-called nebulae, their true nature was unclear. Was it gas clouds inside the Milky Way or independent systems far outside? This question was to prove to be one of the most decisive turning points in the history of astronomy. The key to the answer lay in increasingly precise observations and new methods of distance determination. Edwin Hubble played a central role in this. With the help of powerful telescopes, he succeeded in identifying individual stars in certain nebulae in the 1920s, in particular so-called Cepheids, a special type of variable star. These stars have a special property. Their brightness fluctuates in a regular rhythm, and from this period their actual luminosity can be determined. By comparing the actual luminosity with the observed brightness, Hubble was able to calculate the distance of these stars. The result was astounding. The nebulae in question were much further away than would be possible within the Milky Way. This made it clear that these are not gas clouds within our galaxy, but independent star systems, now known as galaxies. This realization fundamentally changed the understanding of the universe. The Milky Way was no longer the entire universe, but only one of countless galaxies. The cosmos suddenly became unimaginably large. What was previously considered the edge of the universe was now only a small part of a much larger whole. But Hubble's discoveries went even further. He studied the light from distant galaxies and found that it was shifted towards the red end of the spectrum. This so-called redshift indicates that the galaxies are moving away from us. The farther away a galaxy is, the stronger this shift is. From these observations, Hubble developed one of the most important findings of modern astronomy. The universe is expanding. Galaxies do not move randomly, but systematically move away from each other. Space itself appears to be expanding, so the distances between galaxies increase over time. This discovery had profound consequences. If the universe is expanding, then it must have been denser and more compact in the past. This gave rise to the idea that the universe could have had a beginning, a thought that later led to the development of the Big Bang theory. The idea of a dynamic universe was in stark contrast to earlier models, which assumed a static, unchanging cosmos. Even Albert Einstein had originally assumed a static universe and adjusted his equations accordingly. It wasn't until Hubble's observations became known that he realized that his original theory actually allowed for an expanding universe. With the discovery of expansion, the universe became a place that is constantly changing. It has a history, a development, and possibly an end. This new perspective opened up completely new questions. How did the universe come into being? How is it developing? And what determines its future? At the same time, the structures within the galaxies were also examined in more detail. Astronomers realized that galaxies themselves are complex systems, consisting of billions of stars, gas, dust, and possibly still unknown components. They differ in shape, size, and composition. Some are spiral-like, others elliptical or irregular. This diversity shows that the universe is not only large, but also structured. It does not consist of an even distribution of matter, but of complex patterns and hierarchies. Galaxies form groups and clusters, which in turn are part of even larger structures. The universe is a network of matter that extends over enormous distances. Another important advance has been the improvement of observation techniques. Telescopes became more and more powerful, and new technologies made it possible to observe in other wavelengths, for example in the infrared or radio range. This allowed astronomers to discover objects that remain hidden in visible light. These new perspectives led to further discoveries, such as quasars, extremely luminous objects that are located at great distances and release enormous amounts of energy. They, too, help to broaden the picture of the universe and clarify its complexity. Chapter 11 thus marks one of the greatest leaps in the history of astronomy. It is the moment when the universe reveals its true greatness. Not only is the Earth not in the center, it is part of a planetary system that is located in a galaxy that is only one of billions. This finding not only changes scientific understanding, but also people's perspective on themselves. The cosmos is no longer manageable, but almost limitless. The human being is no longer at the center, but a small part of a gigantic system. But at the same time, this realization also opens up a new form of connection. If the same physical laws apply everywhere, if stars and galaxies are made of the same elements as we are, then we are part of this universe, not separate from it, but created from it. The discovery of expansion also shows that the universe is not static, but evolving. It has a past, a present, and a future. This temporal dimension makes astronomy a science that studies not only spaces, but also processes. With Chapter 11, we reach a point where the universe not only gets bigger, but also more dynamic. It is a place of movement, change, and development. And the more we learn about it, the clearer it becomes. Our journey through the cosmos has only just begun. Chapter 12, Relativity and Modern Physics, Space, Time, and a New Reality. With the discovery that the universe is expanding and consists of countless galaxies, the image of the cosmos had already changed fundamentally. But in the early 20th century, an even more profound revolution followed, one that shook not only our understanding of the universe, but also our very idea of space and time. At the center of this change was a man whose name is now inextricably linked with modern physics, Albert Einstein. Einstein challenged one of the most fundamental assumptions of classical physics, that space and time are absolute quantities. In the Newtonian world, space was a fixed stage on which events took place, and time passed evenly and independently of everything else. But Einstein realized that this idea does not correspond to the observations, especially not to the properties of light. In 1905, Einstein published his special theory of relativity. It is based on two simple but radical principles. First, the laws of physics are the same in all uniformly moving systems. Second, the speed of light is constant, regardless of how fast the source or observer is moving. These assumptions led to surprising consequences. Time is no longer absolute, but relative. Two observers moving differently can measure the same period of time differently. Lengths also change depending on the movement. Space and time are not separated, but connected to each other. They form a common structure, space-time. These findings were difficult to accept at first, as they contradicted everyday experience. but they were confirmed by experiments and proved to be indispensable for understanding many physical phenomena. They were to play a decisive role, especially in astronomy. Einstein, however, went even further. In 1915, he published his general theory of relativity, which offered a completely new view of gravity. While Isaac Newton described gravity as a force acting between masses, Einstein interpreted it as a property of spacetime itself. According to this theory, mass curves spacetime, and this curvature determines how objects move. A planet does not follow an invisible force, but moves along the curved structure of spacetime, which is caused by the mass of the Sun. This idea is hard to imagine, but it explains many observations with astonishing accuracy. A famous example is the deflection of light by massive objects. When light passes by a massive body like the Sun, it is easily deflected, an effect that was first confirmed during a solar eclipse in 1919. This observation suddenly made Einstein world famous and impressively confirmed his theory. The general theory of relativity had far-reaching consequences for astronomy. It made it possible to describe extreme phenomena that could not be explained with classical physics. These include black holes, regions in space where gravity is so strong that even light cannot escape. The existence of such objects was initially predicted only theoretically, but over time, astronomers found more and more evidence that they actually existed. Today, black holes are considered central components of many galaxies and play an important role in the development of the universe. Another important aspect of the theory of relativity is its connection to cosmology, the science of the entire universe. Einstein's equations describe not only local phenomena, but also the structure of the universe as a whole. They show that the universe does not have to be static, but can expand or contract. This finding fit perfectly with the observations of Edwin Hubble, who had shown that galaxies were moving away from each other. Thus, the general theory of relativity became the basis of modern cosmological models. It made it possible to describe the evolution of the universe, from a dense initial state to its current structure. But modern physics not only brought answers, but also new questions. Especially on very small scales, for example in the range of atoms and particles, it became apparent that classical physics is not sufficient. This is where quantum mechanics was born, another revolutionary field that describes nature at a fundamental level. Quantum mechanics and the theory of relativity are among the most successful theories in physics, but they are difficult to reconcile. While the theory of relativity describes large structures and gravity, quantum mechanics deals with the smallest building blocks of matter. A unified theory that combines both fields is still one of the greatest goals of physics today. Despite these open questions, modern physics has enormously expanded our understanding of the universe. It shows that space and time are not fixed and unchangeable, but dynamic and interconnected. It describes a universe that is evolving, changing, and characterized by complex interactions. Chapter 12 thus marks a profound change in our worldview. It is no longer just about the positions of stars or the movement of planets, but about the basic structure of reality itself. Space, time, energy, and matter become central concepts that describe the universe in all its dimensions. But perhaps the most important insight of this time is a philosophical one, that our intuition is not always sufficient to understand nature. Reality can be different from what it appears at first glance. It can be complex, surprising, and sometimes even paradoxical. Einstein himself once said, "The most beautiful thing we can experience is the mysterious." And it is precisely this secret that drives astronomy to this day. With every new theory, with every new discovery, we get a little closer to understanding the universe, and at the same time realize how much is still unknown. The theory of relativity has shown us that the universe is not only larger than we thought, but also much more unusual. And that's exactly what makes it so fascinating. Chapter 13, The Age of Space, New Perspectives on Space. Until well into the 20th century, our understanding of the universe was based on observations from Earth. Telescopes, photographs, and spectroscopy had made it possible to analyze stars, planets, and galaxies. But despite all this progress, we remained limited to the view from our planet. Atmospheric disturbances, light pollution, and the limits of the visible spectrum limited our observations. It was not until the beginning of the age of space travel that a completely new dimension of astronomy opened up. We could now view the universe directly from space. The beginning of this era falls in the middle of the 20th century, in a time of great technological and political upheaval. The space race between the United States and the Soviet Union was not only a geopolitical event, but also a scientific breakthrough. With the development of powerful rockets, it became possible for the first time to take instruments and people beyond the Earth's atmosphere and observe them there. A decisive moment was the launch of Sputnik 1 in 1957 by the Soviet Union. This was the first artificial satellite to orbit the Earth, and it marked the beginning of a new era. Suddenly, it was possible to bring measuring instruments into an environment that was free of atmospheric distortions. The door has been opened to more precise observations, new wavelength ranges, and unexpected discoveries. Only a few years later, the first man in space followed, Yuri Gagarin, who orbited the Earth in 1961. The idea that humans could enter space themselves revolutionized not only scientific thinking, but also the perception of the cosmos. The view from above showed the Earth in its entirety, a fragile sphere surrounded by the infinite darkness of space. This new image shaped not only astronomy, but also environmental and social policy. With the first satellites and manned missions, specialized instruments also came into space. Telescopes orbiting the Earth could now pick up light at all wavelengths, from ultraviolet and infrared to X-rays and radio waves. These wave ranges are not accessible from the Earth's surface, as the atmosphere blocks much of it. Space thus offered the opportunity to observe the universe in its entire spectrum for the first time. A particularly groundbreaking instrument was the Hubble Space Telescope, which was launched in 1990. With its high resolution and observation beyond the Earth's atmosphere, it was able to make details visible that were previously unthinkable. Galaxies, nebulae, and star-forming regions became visible in unprecedented sharpness. Hubble revolutionized the understanding of the structure and evolution of the universe. But space travel not only made new observations possible, but also direct research into celestial bodies. Moon missions, beginning with Apollo 11 in 1969, brought samples of lunar rocks back to Earth, providing direct information about the formation and history of the Moon. Unmanned probes also reached planets such as Mars, Jupiter, and Saturn, mapped their surfaces, analyzed atmospheres, and discovered moons, rings, and magnetic fields. This new data greatly expanded our understanding of the solar system. The diversity of the planets and their moons became visible. Their composition, surface structures, and climatic conditions became measurable. Suddenly, it became clear that the solar system is a complex, dynamic system in which each body has its own history. Another important aspect was the discovery of exoplanets, planets that orbit other stars. Space probes and precision instruments have made it possible to measure the tiny fluctuations in the brightness of stars that occur when a planet passes in front of them. This discovery showed that planets exist not only in our solar system, but everywhere in the universe. This opened up new perspectives on the search for life beyond Earth. Space travel has also expanded our understanding of cosmic rays and particle physics. Instruments on satellites and space probes measure high-energy particles that originate from distant galaxies or the Sun. They provide information about processes that are not reproducible on Earth and expand knowledge about energy transfer, magnetic fields, and particle interactions in space. At the same time, the way data is processed and analyzed changed. With the huge amount of information from space telescopes and probes, digital methods and computers became indispensable. Astronomers developed algorithms to process images, recognize patterns, and run simulations. The combination of space travel and computer science opened up completely new ways of modeling and understanding the universe. Chapter 13 thus shows a decisive turning point. Humanity leaves the Earth not only physically, but also mentally. The cosmos becomes accessible, explorable, and measurable. The sky is no longer a distant object of observation, but a space that we can actively explore. This new perspective is changing not only science, but also the self-image of humans. The Earth becomes visible as part of a vast system that remained hidden for many centuries. The idea of the universe as a static background disappears. Instead, it appears as a dynamic, complex space in which processes take place that we can observe, measure, and understand. Space travel thus opens up a new dimension in astronomy, a dimension in which we not only observe, but also travel, measure, and experiment. Every mission provides new insights. Every probe broadens the horizon. The boundaries of the known are constantly shifting. But at the same time, it becomes clear that the universe is still largely unexplored. Billions of stars, galaxies, and planets are waiting to be discovered. Black holes, dark matter, and dark energy show that, despite all the progress, we only grasp a small part of reality. Space travel has opened our eyes, but it has also shown how much is still unknown. Chapter 13 makes it clear that astronomy is no longer limited to Earth. It is becoming a global, even interplanetary science that connects people, technology, and knowledge. The view into space changes our understanding of natural laws, of space and time, of the origin and development of the universe. Space travel opens up new perspectives on space, and at the same time on ourselves. We realize that we are part of a vast system that is infinitely complex, dynamic, and fascinating. The exploration of space thus becomes not only a scientific, but also an existential journey that redefines our position in the universe. Chapter 14: Dark Matter and Dark Energy, the Invisible Forces of the Universe. Despite the enormous advances in astronomy and physics made over the centuries, the universe still remained full of mysteries. Even in the 20th century, after the discoveries of galaxies, planets, black holes, and the expansion of the cosmos, it became apparent that we could only see or measure a fraction of reality directly. A particularly profound mystery arose when astronomers began to analyze the motions of galaxies and galaxy clusters in more detail. Much of the matter in the universe appeared to be invisible. This mysterious substance was later referred to as dark matter. The discovery of dark matter began with observations of galaxies by the Swiss astronomer Fritz Zwicky in the 1930s. Zwicky studied the Coma galaxy cluster and found that the visible mass of the galaxies was not sufficient to explain the observed movements of the clusters. In other words, there had to be an invisible mass that exerted additional gravity. He coined the term dark matter, even though his idea received little attention in his time. Decades later, further observations confirmed that dark matter is a fundamental part of the universe. Stars within galaxies moved faster than could be explained by visible mass alone. Spiral galaxies showed rotation curves that indicated an additional, invisible mass. Without this dark matter, the galaxies would break apart. Their own gravity was not enough to hold them together. But dark matter is not only invisible in the sense of light. It apparently hardly interacts with electromagnetic radiation. This means that it neither reflects nor emits light, which explains why we can't see it directly. Their existence is proven exclusively by their gravitational effect, by the movement of stars, gas clouds, and galaxies. At the same time, astronomers discovered an even more mysterious phenomenon towards the end of the 20th century, so-called dark energy. While the expansion of the universe was previously known, it has now been shown that it is accelerating. Instead of slowing down due to gravity, galaxies are moving away from each other faster and faster. This acceleration suggests that a kind of repulsive energy is at work, an energy that permeates space itself and drives expansion. This invisible force was called dark energy. Dark energy accounts for about 68% of the total energy matter content of the universe, while dark matter accounts for about 27%. Visible matter, everything we can see, from stars to planets to gas clouds, makes up only about 5% of the entire universe. This was a shocking realization. What we are directly observing is only a tiny part of the true universe. The discovery of dark matter and dark energy raises profound questions. What exactly are these invisible components? How do they interact with visible matter? How did they influence the formation of galaxies and structures in the cosmos? Many theories have been developed, but so far there is no conclusive answer. Dark matter could consist of previously unknown particles that interact only weakly with ordinary matter. Dark energy could be a property of empty space itself, a kind of cosmological constant that drives space. The search for answers is one of the greatest adventures of modern astronomy and physics. Experiments on Earth, for example in underground laboratories, try to detect dark matter directly. Space probes and telescopes measure the structures of the universe to get clues about the nature of these invisible forces. Each discovery provides new data, but at the same time further questions open up. The complexity and scale of these invisible components exceed our previous imagination. The realization of dark matter and dark energy shows that our understanding of the universe is still incomplete, despite all the advances. It is a reminder that there is much more to the universe than we can see directly. The visible world, stars, planets, clouds of gas and dust, is only the tip of a huge iceberg. Most of the cosmos remains hidden from us, and we can only grasp it through indirect measurements and theoretical models. These discoveries also fundamentally change cosmology. In the past, the universe was a relatively tangible system that could be explained by stars, galaxies, and gas. Today we know that the universe is shaped by invisible forces that determine its development, structure, and future. Without the consideration of dark matter and dark energy, no realistic model of the cosmos would be possible. Dark matter and dark energy also have implications for the future of the universe. They influence whether the universe expands forever, whether it contracts again at some point, or whether it will end in an endless big freeze. These questions are among the greatest open mysteries of modern science. Chapter 14 thus shows a crucial point. The more we learn about the universe, the more we realize how much is still unknown. Astronomy has taken us from the first stars in the night sky, to the discovery of planets, galaxies, and black holes, to the invisible forces that shape the entire universe. But the picture remains incomplete, and it is precisely this incompleteness that drives scientists on. The study of dark matter and dark energy is also a mirror for human curiosity. It shows that we are willing to expand our thinking, question theories, and think beyond what is directly visible. Astronomy thus remains not only a science of the stars, but also a science of the unknown, the invisible, the mysterious, the yet to be discovered. This chapter makes it clear: the universe is bigger, more complex, and more mysterious than we ever thought. The visible world is only a fraction, and the invisible forces dominate the cosmos. But it is precisely this invisibility that opens up space for new questions, new theories, and new discoveries. The search for the invisible is driving astronomy into the 21st century and beyond. Chapter 15: The Future of Astronomy, Departure into Unknown Worlds. The history of astronomy, as we have traced it in the previous chapters, is a history of constant expansion of knowledge, from the first observations of the night sky, to the precise laws of Johannes Kepler and Isaac Newton, to the modern discoveries of galaxies, dark matter, and dark energy. But even after all these discoveries, one thing remains clear: the universe is far larger, more complex, and more mysterious than we could ever imagine. Astronomy today stands on the threshold of a new age, an age characterized by technology, interdisciplinary research, and immeasurable curiosity. A central aspect of the future of astronomy is the study of exoplanets, planets outside our solar system. Since the discovery of the first exoplanet in the 1990s, the number of these distant worlds has increased to thousands. With increasingly sensitive telescopes and instruments, astronomers can not only measure their orbits, but also study atmospheres, determine temperatures, and analyze chemical compositions. The search for Earth-like planets in the habitable zone, the area where liquid water could exist, has become a central goal. This research could one day provide answers to what is probably the most fundamental of all questions: is there life beyond Earth? At the same time, new telescopes and observatories are opening up completely new perspectives. The James Webb Space Telescope, launched in 2021, works in the infrared range and makes it possible to observe objects that were previously invisible. It can detect distant galaxies that formed shortly after the Big Bang, and thus take a look at the earliest phases of the universe. Upcoming projects such as the Extremely Large Telescope (ELT) on Earth also promise to push the boundaries of what can be observed once again. However, the future of astronomy depends not only on powerful instruments, but also on the processing of large amounts of data. Modern observatories provide gigantic amounts of data that can only be analyzed by advanced computers, artificial intelligence, and machine learning. AI-powered algorithms help recognize patterns, discover new objects, and perform complex simulations of the universe. The combination of human intuition and machine computing power opens up new possibilities that were previously unimaginable. In addition to the discovery of new objects, the focus is also on the investigation of fundamental physical processes. Dark matter and dark energy remain largely unexplored, and the question of how they shape the universe remains central. Advances in particle physics, new laboratory experiments, and space observatories could provide crucial clues in the coming decades. Perhaps we will even fully understand the nature of these invisible forces, thus closing the last major gaps in the cosmological model. Another exciting area of the future is the direct exploration of planetary systems and celestial bodies. With probes reaching distant planets, moons, and asteroids, we can directly study the composition, geological processes, and potential habitability of these worlds. Missions to Mars, Europa, Enceladus, or Titan have the potential to fundamentally change our image of life in the solar system. Perhaps we will discover evidence of microscopic life or even biological processes, an event that would revolutionize astronomy and all of humanity. The conceptual understanding of the universe will also evolve. With the discovery of gravitational waves, black holes, and extreme astrophysical events, astronomers can now study phenomena that were unimaginable just a few decades ago. The combination of electromagnetic observation, gravitational wave detection, and neutrino astronomy opens up a new era of multi-messenger astronomy, in which an event is analyzed from different senses. This allows for a much more detailed understanding of cosmic processes and the mechanisms that shape the universe. In addition, interdisciplinary research will play an increasingly important role. Astronomy today is closely linked to physics, chemistry, computer science, biology, and even philosophy. The search for life outside of Earth requires knowledge from biology, while understanding gravity and energy is impossible without physics. Computer models help to simulate cosmological developments, and chemical analyses enable the study of distant atmospheres. As a result, the picture of modern astronomy has become global, interconnected, and extremely complex. The future of astronomy is also closely linked to the internationalization of research. Large observatories, space missions, and projects such as the James Webb Telescope or the Square Kilometre Array radio observatories are international undertakings in which scientists from all over the world work together. No country today can fully unlock the secrets of the universe on its own. This global collaboration accelerates progress and enables projects that would not be feasible on their own. A particularly fascinating aspect of future astronomy is the exploration of distant and early epochs of the universe. The observation of galaxies formed shortly after the Big Bang allows insights into the formation of stars, planets, and cosmic structure. By studying these early stages, astronomers can understand how the universe became what we see today, a massive, ever-evolving structure made up of billions of galaxies. In addition, the future also opens up the possibility of direct interstellar exploration. Concepts such as small laser-accelerated probes that could travel to nearby stars in a few decades are theoretically conceivable today. Such missions would make it possible to explore exoplanets directly, analyze their atmospheres, and perhaps find evidence of life. Even though these projects are extremely technologically challenging, they show that the limits of astronomy are not limited to the Earth or the solar system. Finally, Chapter 15 makes it clear that astronomy is always a science of looking ahead. Every new technology, every new discovery opens up new questions and broadens horizons. While previous generations explored the movements of stars and planets, today we focus on complex structures, fundamental forces, and potential life in distant worlds. The universe remains an infinite mystery, a field of research that will never be fully completed. The future of astronomy is therefore also a human story, the story of curiosity, creativity, cooperation, and tireless research. It shows that despite all the progress, we only know a fraction of the cosmos at a time, and that the rest challenges us to continue searching, observing, and learning. But it is precisely this uncertainty that makes astronomy so fascinating. It is a constant journey that takes us from the first glimpse of the stars, through the discovery of planets, galaxies, dark matter, and energy, to modern telescopes, space probes, and interstellar dreams. It teaches us that our place in the universe is small, but not insignificant, that we are part of a gigantic dynamic system far beyond our imagination. The future holds countless possibilities. We are on the cusp of new discoveries that will once again change our perspective, from the nature of dark matter, to the mechanisms of dark energy, to the discovery of alien life and the direct exploration of other star systems. Astronomy will continue to be the gateway to infinite curiosity, knowledge, and wonder, and will lead humanity into an era in which the universe is no longer just observed, but actively understood and explored. The journey that began thousands of years ago with the first glimpses of the night sky is far from over. On the contrary, it has only just begun. Every generation, every new technology, and every new discovery opens up new paths, new questions, and new wonders. And so astronomy remains the greatest adventure that mankind has ever undertaken, an endless journey through space, time, and knowledge.